Then bang! And the universe blossomed in all directions, and the universe's finite energy was born. There was one universal force at the time called supergravity, which immediately separated into two forces: the fundamental gravitational force and the grand unified force, fundamentally comprising of the strong, weak, and electromagnetic forces. Quarks arise when the strong force is then distinguished from the electroweak force when the temperature cools to 1 trillion Kelvin due to the expansion of space. Upon further spatial inflation, the temperature cools to 10 billion Kelvin, and now it has only been 1 second since the Big Bang. Quarks start to coalesce to form protons and neutrons because of the strong force. The recombination phase eventually begins at approximately 400,000 years at temperatures of 4000 Kelvin. When an electron and a proton electromagnetically bond, they create a neutral hydrogen atom. This process is called electron capture. These electrons quickly de-excite to their ground state by emitting photons in a process called photon decoupling. These photons define the cosmic microwave background radiation, which is approximated to 2.7 Kelvin.
Eventually, these atoms form clouds of interstellar gas and dust, called diffuse nebulae, which are mostly composed of hydrogen and helium. These are considered stellar nurseries as star formation takes place here. If the gravitational attraction is greater than the force arising from the gas pressure, the cloud will collapse on itself and eventually form a protostar. Inside the star, a hydrostatic equilibrium is established, which means that the star's internal pressure is balanced by its gravitational pull. Stars evolve through different stages, which can be summarized on a Hertzsprung-Russell or HR diagram. This diagram is a plot of stars by their luminosities, i.e. brightness, versus their surface temperature or spectral class. Most of the stars lie on the main sequence and produce energy by fusing hydrogen inside their core. Let's look at the Sun's journey on the HR diagram. The mass of the Sun is defined as one solar mass. After the protostar has been born, it enters the main sequence phase after billions of years, where hydrogen fuses into helium over 10 billion years. Once the hydrogen in the core has been exhausted, the Sun grows into a red giant, where its luminosity significantly increases. The hydrogen then moves to the outer shell, known as the envelope. At the end of the red giant phase, a helium flash occurs in the core, where a part of helium fuses into carbon. This process continues through the horizontal branch phase. Then a helium envelope forms, which starts to fuse until reaching the asymptotic giant branch phase. After some other processes, eventually the outer shells are pushed away and the planetary nebula forms. The final, naked core will be a white dwarf with half solar mass.
Stars with a birth mass of less than 8 solar masses will never form an iron core and will not become supergiants, as they cannot fuse carbon and heavier elements as they have less gravitational pressure. Let us consider the case of a larger star, of between 8 and 25 solar masses. Stars this large quickly fuse hydrogen into helium in their cores. They then grow into red supergiants, which are many times bigger than red giants. After this, they continue to fuse heavier elements until they are left with only an iron core. The iron in the core cannot go through nuclear fusion, so the core grows until it reaches a distinct mass called the Chandrasekhar mass of around 1.44 solar masses. Once the core reaches this mass, it cannot support itself anymore and undergoes a gravitational collapse, exploding into a supernova. The collapsed core then forms a neutron star, a very small and very dense type of star which cools over time. Stars that are larger than 25 solar masses go through a very different route. After exploding into a supernova, if the core has a mass greater than the Tolman-Oppenheimer-Volkoff limit of 2.17 solar masses, it evolves into a black hole instead of a neutron star. A black hole is a region so dense that nothing, not even light, can escape its gravitational pull.
A collection of stars and cosmic materials gravitationally bound together is known as a galaxy. Their formation still remains a mystery. This is an example of a spiral galaxy, which is disk-shaped object with spiral arms and a dense center, called the central bulge. Here is another example of a spiral galaxy viewed axial. A system of galaxies is called a cluster, and here is an image of the Perseus cluster. Hundreds of billions of galaxies make up the universe, but is that it? Is there more? Is there another universe? Will the universe keep on expanding or will it collapse? What do you think?
Dun 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 dun